All right, I'm going to go ahead and narrate the solutions to those remaining four problems as well, so that if you're having problems or you're not sure how to go through it, you can watch this to see the process. Okay, so Talitha is using the faucet to force water into a balloon at a rate of 2 cubic centimeters per minute. So first thing, I'm going to go ahead and draw my picture. Here's my balloon. I'll leave some space here for the water to be coming in. Here's the water coming in at 2 cubic centimeters per minute. You know it's not a perfect, excuse me, it's not a perfect sphere, but you get the idea. Assuming that the balloon shape remains spherical, find the rate of change of the surface area. So I'm going to go over here and start my chart. Rate of change of the surface area. So that means I'm going to add something to my chart about surface area because I'm concerned about surface area. I'm going to call that dSA dt equals, we don't know. That's what we're trying to find. I'm going to circle that. That's the one we're trying to find. I'm also going to put surface area in here. We don't know that from the problem either. We're not given the surface area. Okay, find the rate of change of the surface area of the balloon when the radius is 7 centimeters. So the radius here of the balloon is 7 centimeters. 7 centimeters. Okay, I'm going to add that to my chart. R equals 7. Now, when I add this, I'm also going to add dr dt equals, and anything else in my problem, that 2 cubic centimeters per minute. Is that telling me how fast the radius is changing? No, not at all. That's telling me something different. So what is that 2 cubic centimeters per minute? Think about cubic measurements, cubic centimeters. What would you be measuring there? If you were measuring something in cubic feet or cubic meters or cubic anything, you're measuring volume. So cubic centimeters per minute, that's how fast the volume is changing. So we know dV dt equals 2, and the actual volume, another question mark. Wow, that's a lot of question marks right there. That is a lot of question marks. Do we need to find all of them? Maybe, maybe not. We don't know yet. What we should do next, though, is set up the equation that's going to help us find this one that we circled right here. We want to find that one. So we need to set up the equation that's going to help us to find that one. And that's the derivative of the surface area, the rate of change of the surface area. So the equation I'm going to use is the surface area equation. Surface area equals 4 pi r squared for a sphere. Surface area equals 4 pi r squared. Okay, I'm going to segment my board here. All right, so now I'm going to take the derivative of this. And remember, everything is a function of time, so this becomes dSA dt equals 4 pi, that's just a constant, 4 pi times 2r dr dt. I had to use chain rule there because r is a function of t. Now, dSA dt, do we know that? We look over here, we see no, we do not know that, and that's okay. That's the one we're trying to solve for. We want to leave that as a variable. R, do we know that? Yes, we know an R value, so we can plug that in. dr dt, do we know that? No, we don't have anything over here. So I'm going to plug in for R. So I've got dSA dt equals 4 pi. Actually, I'm just going to go ahead and make this 8 pi. 8 pi times 7 times dr dt. Okay, now I've got to find something to plug in for dr dt. I've got to use my extra information here to find something to plug in for dr dt. Well, what haven't we used yet? What have we not used yet over here? We haven't used this dv dt number. So maybe there's some way we can use this dv dt number to help us find dr dt. Well, let's get an equation that has dv dt in it. In order to do that, let's start with the volume equation. V equals 4 thirds pi r cubed. The volume equals 4 thirds pi r cubed. Do I need to find what V equals? No. Is dr dt in this equation right now? No, it's not in this equation. So I can't plug in and solve for dr dt, but I can take the derivative here. And when I take the derivative, I get dv dt equals, I'm going to get 4 pi r squared dr dt. Because the 3 from the r cubed is going to come down and it's going to cancel out with the 3 and the 4/3. And I have to do the chain rule, so that's where I get dr dt. Now, we've got a value for r. We've got a value for dv dt. So I can plug in here. So I'm going to do that. I'm going to plug in for dv dt. I'm going to plug in 2 equals 4 pi, and then r, I believe, was 7. 7 squared dr dt. Okay, so now I go ahead and I multiply everything out here, and I'm going to get 2 equals 7 squared is 49 times 4. Well, we're right under 200, so it's 196 pi dr dt. And so dr dt equals 2 over 196 pi, so that's 1 over 98 pi. So that's our value for dr dt. This is similar to those ladder problems where we had to use the Pythagorean theorem, that equation, to find our missing variable. Only here we had to use even a derivative equation. We had to set up an equation and take a derivative because we needed a dr dt, and that was the only way we were going to get a dr dt in our equation. And we had some known information about dv dt that we needed to plug in. So we needed to have an equation that had dv dt and dr dt in it. Okay, so now let's go ahead and take our dr dt and plug it on in over here. So this is going to come on up. So I've got dsa dt equals 8 pi times 7 times, and I'm plugging in 1 over 98 pi. Okay, so dsa dt equals 8 times 7 times pi is 56, right? 56 pi over 98 pi, which 56 over 98, let's just start simplifying, becomes 28 over 49. 28 over 49. Can we simplify that? 7 goes into both of them, equals 4 over 7. Okay, 4 over 7, and this is dsa dt. So our units here, we're talking about surface area. If you know what surface area is measuring, and we were in centimeters and minutes here, this is going to be centimeters squared per minute. 4/7 centimeters squared per minute. All right, I'm going to pause it here for 1 second. All right, we're all good. 4/7 centimeters squared per minute, or square centimeters per minute. So that is number 1, done. Now number 2, I just put the answer back up here. I'm going to just scroll through it real quickly. If you need to see this one, you can go ahead and pause it right now so you can check your work. I'm not going to explain it again since I already explained it in the other video. You can go back to that video if you want to hear the explanation here. All right, on to number 3. Andrea is walking straight away from a 15-foot tall lamppost. I'm going to start drawing my picture right away. There's my lamppost, 15 feet. Andrea in stilettos is 6 feet tall, so she's walking away. So we'll put her over here, make sure she lines up on the ground. 6 feet tall, and she can walk at a rate of 4 feet per second. How fast is her shadow lengthening when she's 20 feet away from the post? So this right here, we're going to have some distance right here. We'll call this, let's call this x. This is changing. I'm going to give it a variable name. And then her shadow, how fast is her shadow lengthening? Well, her shadow will be right here. I'll call that y. Now I'm going to draw in an auxiliary line. That's a line that's not in the problem, but makes it a little easier to solve the problem. Here it is, right here. Guess I need to extend y a little bit. There it is right there. So that gives us a couple of right triangles. If you see, we have 2 right triangles here, and they are inside of each other. When they are like this, they share a common vertex right here. when they share a common vertex and they're right triangles, that means they are similar triangles. And when we see this setup with similar triangles, your first thought should be proportion. So let's, I'm jumping ahead of myself. Let's start writing down some values that we know. We know in our problem that we want x to be what? How fast is it lengthening when she's 20 feet away from the post? 20. And we want, what is dx dt then? Dx dt is, how fast is she walking away? That's how fast x is changing, 4 feet per second. Okay, now y, do we know the length of y? No, we don't know that. Dy dt, how fast is y changing? Well, y over here, that is her shadow. So that is what we want to figure out. We want to figure out dy dt. Okay, so we've got these values. We've got the other values in the picture. We need to set up a proportion here. So the proportion is we match the corresponding side. So first of all, we match this side with this side. Maybe I'll use a different color there so you can see it. I'll use green. Oh. We match this side here with this side. So in our proportion, we've got 15 over 6. All right, so that's the start. And then next in our proportion, we match the long sides. Now this is where people go wrong. We don't just want to match this. This is not the side of any triangle. This is the side of the long triangle. And the length of that is x plus y. We match that with this side of the small triangle, length of y. So 15 over 6, big side over small side equals big side over small side. Okay, so now before I go ahead and take the derivative of this so I can get some dx dt's, dy dt's, I better get some dy dt's in here since that over here, that's what I'm, where's my mouse? That over here is what I'm trying to find. I better take the derivative so I can have some dy dt's. I don't really want to do quotient rule, so I'm just going to multiply both sides by y and both sides by 6, so that I get 15y equals 6x plus 6y. All right, now I'm going to move this a little bit. Actually, I'm going to group it, make it a little smaller. Group, smaller. Put this over here with my picture. That's my equation so that I can divide my board like I've been doing each time. So that's my equation. Okay, now I'm going to take the derivative of that equation. So I get 15 dy dt equals 6 dx dt plus 6 dy dt. So I've got that equation. Let's look. Do I have enough information already to plug in? I think so. If I'm trying to solve for dy dt here, I have enough stuff to go ahead and plug in. So I plug into my problem. What's going in for dx dt? I got to scroll back up real quick. Dx dt is 4. So I have 15 dy dt equals 6 times 4 plus 6 dy dt. Okay, I subtract my 6 dy dt. I've got 9 dy dt equals 24. So dy dt equals 24 over 9. And these are both divisible by 3 equals 8 over 3. And we need to figure out a unit for this. This is how fast y is changing per second. And we're measuring in feet. We're on per seconds. So we've got, this is in feet per second. Now, one thing you may have noticed here is some people may have went ahead right away and been like, oh, I need to get a value for y. If we just go through the process of first taking the derivative of our equation, then plugging in here, and then seeing, do we need to use our equations to get any more values, or are we down to one variable, like we are right here? One variable, one variable. If we're down to that one variable that we're trying to solve for, then we're good to go. We don't need to get any more variable solved for using any equations. All right, good to go on this one. Let's move on. Next one, Lauren is filling a spherical balloon. I already have done this one. It's in the other video. I will scroll here slowly through the answer. And if you need to pause it to check your work, go ahead and do that. Okay, going on to number 5. Ivan is using the faucet to force water into his balloon at a rate of 2 cubic centimeters per second. There's a balloon again. Here's my opening. The water's going in here at 2 cubic centimeters per second. Or per minute, my bad. 2 cubic centimeters per minute. Assuming that the balloon shape remains spherical, find the rate of change of the radius when the radius is 7 centimeters. I'll add in the radius, that's 7 centimeters. I'm going to add some of this stuff over here in a chart. I know r equals 7. dr dt, do I have that in my problem? dr dt. Oh, right there, it says find the rate of change of the radius. So that's what we're trying to find. That's what I want to find. Now this 2 cubic centimeters per minute going in, hopefully if we recall back to an earlier problem, that's dv dt equals 2 centimeters cubed per minute. And volume, do we know the exact volume right now? No, we don't. Okay, so I have some information about the change in volume. I have some information about the radius. I want to get dr dt. So I've got to think of an equation that's going to relate these things. So the first equation that comes to mind, at least for me, is the volume equation. So volume equals 4/3 pi r cubed. All right, gonna break up my board here before I take the derivative. Boom, boom, boom. Okay, the derivative is dv dt equals 4 pi. Well, actually, we've already done this. It becomes, 4 pi r squared dr dt. Now I look at my variables in this problem. dr dt, that's the one I'm going to try to solve for. That's fine to still be a variable. What other variables do I have? R, right there. Do I have a value for r? Yep, so I can plug that in. dv dt, I want to plug something in for that. Do I have a value for that? Yep, so I can plug something in. Okay, so this problem's actually pretty easy. All we got to do is plug right on in. So dv dt is 2 equals 4 pi. Now r is 7 times 7 squared dr dt. Okay, I'm going to give myself a little room down at the bottom. So 7 squared is 49 times 4. That's still 196. So 196 pi dr dt. So dr dt equals 1/98 pi. Better put a unit with that. Oh, I'm going to need to give myself some space there to put a unit. Here, I'll put dr dt equals on the other side. 1/98 pi. And then our units, we're measuring in centimeters, and it was per minute. So this is just centimeters per minute. Okay, that one was fairly straightforward. Let's go on to the next one. Final question. All right. Kyron, I don't know, I didn't write the problem, has left her ice cream in a 9 centimeter tall sugar cone. It's a cone, so I'm going to draw a cone. I'm actually going to draw a 2D version of a cone. 9 centimeters tall. Here's that, that's 9. 9 centimeters tall to melt. It is melting out the bottom at a rate of 1 cubic centimeter per minute. Boom, it's coming out at 1 cubic centimeter per minute. If the diameter of the cone is 6 centimeters, okay, we'll do that across the top here. This is 6 centimeters. Or I'll just put 6 for now, that's fine. We can look back at our problem for units when we're doing our answer. So across the top here is 6. find the rate of change in the height of the melted ice cream when it is 3 centimeters tall. So we've got some ice cream here in our cone. Like right here, here's our ice cream in our cone. And we want to find the rate of change in the height of this melted ice cream when it is 3 centimeters tall. So this right here, this dotted line in green, is 3. Okay, so let's see. Let's start adding some variables over here. Now, the height of the ice cream, height is 3. Now, okay, we've got that. What about dH dt? And for h, remember, we're talking the height of the ice cream, not the height of the cone. The rate, so dH dt is the rate of change in the height of the ice cream. Well, that's exactly what we're trying to find. We don't know that. Okay. What else do we have? We have that this 1 cubic centimeters per minute. Well, that's dV dt equals, this is -1. Yes, -1 because we're losing 1 centimeter per minute. Now, do we know the volume? No, we don't actually know the volume. Okay. What else? We have some things about the height of the cone and the radius of the cone, but those variables are going to change. We're more concerned about the ice cream, so I'm not going to add them to my chart. Now, we've got to figure out what sort of formula we can use to relate these variables that we're given, all in our picture, and the stuff in our chart to get dH dt. Now, I drew a 2D cone for a reason, because what we can pull out here, and I'll draw it on the side. Let me shrink this 1 cubic centimeter per minute here a little bit. 1 cubic centimeter per minute. Well, I'm going to draw it here on the side. What we can pull out is that we've got really this shape in our cone. Well, that's kind of silly. Wish my smartboard wouldn't do that. But you're getting the idea, hopefully. We've got, maybe I'll put that a little lower to match with my picture. We've got this shape in our cone, which is just like our lamppost problem. We've got 2 right triangles where they share a vertex right here, and they're both right triangles, so they're similar triangles. So let me label some of the measurements on here. At the top of my cone, the radius is 3. The height all the way down, oops, I'll make that a little better. The height all the way down is 9. And then the height here just of the ice cream is 3. So just like before, we can set up a proportion to find the radius of the ice cream. Well, we're not sure we need that yet. We're not sure we need that. We're just getting ourselves ready. What equation are we going to use here? Well, we've got dV dt, we want dH dt, so let's go ahead and use volume. Let's go ahead and use volume. Volume equals. Now, volume of a cone. I'm actually going to have to pause this real quick and go find the volume of a cone formula because I don't know it off the top of my head. All right, a quick Google search helped me out, and the volume of a cone is 1/3 pi r squared h. Okay, I believe that's even one that's on your sheet. Okay, I'm going to segment my board here real quick. Now, if I had been doing this problem kind of following my own thought process from before, I probably would not have drawn this part yet. I was getting a little ahead of myself there, just getting a little too excited. So let's go on. Let's go on here. So take the derivative of this formula. You did that on your chart, but just a reminder, it's dV dt equals, and we've got 1/3 pi is a constant multiple. And then with r squared h, they're both r and h are both functions of t, so we're going to need to do product rule with them. But we're also going to need to do the chain rule with r squared. So I'm going to do the first one, r squared, times the derivative of the second, dH dt, then plus the second one, h, times the derivative of the first, which is 2r dr dt. Okay, now remember, we're all talking about the ice cream cone right here. We're all talking about the ice cream cone. What we're going to put in, variables we're going to put in for the ice cream cone. So I'm going to underline in, let's say, in green, any variable that we do have. So dv dt of the ice cream. Sorry, we're talking about variables of the ice cream, of this, for this ice cream, this volume here. This is the volume of this part in green. Volume of this part in green. Not of the whole cone. We care about the volume of the ice cream, which is there in green. Okay, so I'm going to underline variables we do have. We do have the dv dt. We do have the height of the ice cream. We do not have anything else. We do not have r. We do not have dh dt. We do not have, well, there's another r. We do not have dr dt. Well, okay. Some of those are okay, some of those are not okay. dh dt, that's okay to not have, because that's what we're trying to solve for. So I'm going to put a little box around that guy. That's okay to have it. The other ones we've got to figure out. Well, hopefully you've figured out that getting r is not going to be too hard if we use our similar triangles, because r goes right here. So we set up our proportion. 3 over r equals 9 over h, where h is the height of the ice cream cone. Now, I'm going to multiply this and I get 3h equals 9r. And for my little segment of ice cream right here, my h is 3. So I'm going to plug in 3. 3 times 3 equals 9 times r. So r equals 1. R equals 1. We've got that. Awesome. But now, so that gives us an answer for r. So I'm going to give that a green underline wherever I see an r. Got a value for r. We're good to go on that. Now we've still got this dr dt. Now this is a real tricky one right here. Basically, we don't have anything else. Like, we don't have any unused information yet. But if you notice, there's a reason I set this up over here, leaving h and r in the equation instead of plugging in this 3 right away. Because if I go ahead and take the derivative of this, and I'll do this down here. If I go ahead and take the derivative, I'm going to get 3 dh dt equals 9 dr dt. So this is a relationship between dr dt and dh dt. So what I can do is basically I can get dr dt out of my equation, because I can divide it by 9 and get that 1/3 dh dt equals dr dt. So anywhere in my equation that I see a dr dt, I can now substitute in 1/3 dh dt. So that means right here where this dr dt is, I can substitute in a 1/3 dh dt, and now I'm only going to have dh dt as my variable remaining in my equation. All right, let's go ahead and substitute everything in. So dv dt, -1 equals 1/3 pi. Now r was 1, right? I swear I'm going to get some variable wrong and have to go back and do all of this again. 1 squared dh dt plus, now h was 3. 3 times 2 times 1 for r times 1/3 dh dt. Okay, so I substituted everything in right there. Now it's time, now it's just time to simplify. I'll try and leave some of this showing here. Okay, so then I'll leave my -1 equals 1/3 pi. I'm just going to simplify in the parentheses here. So I've got 1 squared dh dt, that's just dh dt, plus, well, this 3 and this 1/3 are going to make a 1, so plus 2 dh dt. So that's going to be 3 dh dt, right? And then we have times 1/3, 3 dh dt, and we're going to have times 1/3. So I'm going to have -1 equals Now I'll even write it all out. 1/3 pi times 3 dh dt. -1 equals 1/3 and 3. We get pi dh dt. And so finally, we got the answer. dh dt equals -1/pi. And let's go back. Let's remember we got to add some sort of units. I always forget to leave space there. -1/pi. And dh dt is how the height is changing, what we're measuring in centimeters. So it's -1/pi centimeters per second. All right, that was a very tricky one. Very tricky one in that we didn't have another equation, so we had to basically make a substitution there. If you go through this process of finding the equation that you want, that is the volume equation, and then taking its derivative, and then being like, how do I get all of these variables, these ones that were underlined in red, these ones that I don't want in there, how can I solve for them? What can I possibly do? How can I use my given information? That's the thought process that you need to go through each time. And the only given information we had was this set of similar triangles. So we have this equation. So that let us solve for r. But it was also an equation that related h and r. So if we took its derivative, it would relate dh dt and dr dt. So you had to be a little clever to find that one out. Props to you if you did. Okay, hopefully you found these answers useful. If you have questions, feel free to come in and ask me. Have a good rest of your day.